Hello, I'm going to talk a little bit about a tool I wrote for a kernel project I'm working on. And it's a tool that generates a bootable EFI image. And the reason I wrote it was because I work on Windows and I can use WSL and I can use a Linux VM if I want to, but I kind of wanted a nice, easy way to generate, given a single boot kernel image, just create the disk with the correct layout and partitioning, and have that as part of my Windows build process. I looked around, couldn't really find any tools that did this on Windows without being quite fiddly, and since it's a pet project, I didn't really care about shaving a yak, so I kind of went on and did it. So I'm just going to talk a little bit about it because, you know, there's some stuff in here that might be interesting for others who want to do the same thing. There is a lot of standards documents to be read, so hopefully maybe I've done some of that work for you if you're interested. So what we're looking at is the basic sort of simple tool Efi Gen that takes a boot image, which is a bootx64.efi file. That's a PE executable. I won't talk about the details of EFI right now. That's perhaps for a different broadcast, but the point being that's your executable. And it builds a directory structure in this image, which needs to be of a particular type. It needs to have a particular type of master boot record, a particular type of partition, and it needs to be a FAT file format, that partition in which the data lives. And it builds a directory structure which has a EFI root directory, a boot directory called boot underneath that, and underneath that again is the bootx64 EFI, which you see here. Alright, so before I do that, before I go into the code, I'm just going to quickly take you through, very quickly, the FAT file format. So the FAT file format is going to be used for the actual partition in which this data lives. And there are three different types of FAT file format. There are FAT32, FAT16, and one that's not in this picture called FAT12. And there is a huge amount of documentation. There's a great document, there's a link to it later on. It's a great document published by Microsoft which contains all the nitty-gritty details of how this file system works. And I must admit, one thing I didn't know was that the only way to determine whether something is FAT16, FAT32 or FAT12 is by counting the amount of clusters available on the drive when the partition. So it doesn't even have to do with the total size of the disk. It has to do with how you partition up that disk, right? Clusters obviously contain sectors, so depends on how many sectors you have per cluster, and sectors have different sizes. They can be 512 bytes, they can be 4K even if you wanted to. But there is no flag inside of the partition. There's no, you know, structure with an entry saying I'm FAT32, I'm FAT16. You actually have to calculate that using a heuristic, and I'll show you that heuristic a little bit later on. Anyway, the two file formats that I'm going to consider here are FAT16 and FAT32, because one thing that is certain for the file sizes that I'm looking at, and this is a very specific implementation, it's not a generic implementation, but for the file sizes I'm looking at, it's only going to be FAT16 or FAT32. So it's going to be larger than a floppy disk by some margin, or much larger than a floppy disk, which is when you switch to FAT32. The basic layout you see here, there are these pieces of reserved or specific for the type of file format, sectors or regions, and then the green regions here on both sides are where your data lives. Now, I'm not going to go into all the detail of this. What I'm going to point out though is there is one fundamental difference between FAT16 and FAT32, and maybe you can see it. The root directory in FAT16 is part of the reserved area. So it has a fixed number of sectors allocated to it. And you allocate that when you format the disk. In FAT32, the root directory is like a normal file. It just happens to be the first one, which means it has a cluster chain, which means that it can grow, which means that it can be as big as you like. So with FAT32, it's a more efficient system because you don't know how many files you're going to have in your root directory, and your root directory can handle any number of files. Whereas with FAT16, the root directory has a fixed size up front. You have to sort of make a guess how big you might need it to be, and you can only, if you try to add more files to to your root directory, that won't work beyond that. So that's a key difference between these two guys. Just a brief reminder, FAT files in the FAT file system are stored in a cluster chain. A directory entry points to the first cluster, which points to the next cluster, and the next cluster up to the nth cluster, and then the nth cluster points to a cluster entry, which is EOC, or end of chain. And the total size of the file is the sum of bytes taken up by all of these clusters. Simple as that. All right, fine. So let's go back to the code. There is some stuff here which is not particularly relevant. That's just for the tool. But I'm going to go to the function called the create Efi boot image. Now I'm not going to talk about the too much about the Efi layout. It's actually quite simple. There is a something called a protective master boot record. Then there is a GPT, so a GUID partitioning, so partitioning and a disk which is identified by GUIDs, and then there's a list of the different partitions on the disk. In our case, there's only going to be one, and then there is the partition itself, which is going to be the one that we have created and we format for as FAT. And then at the end of the disk, there is a backup area which is used to recover if there's an error with the initial bit here, then you can recover it. A disk repair tool can recover it from the back here. All right, so this create Efi boot image just does that. It creates the file. It does some rounding up to sizes. In this case, I've made it simple for myself, and I'm just basically rounding up to the nearest 128 megs. One thing I'm using, and that's kind of key for Efi, is I'm using a sector size of 512 bytes. That's a standard thing. Efi can support other sizes, but it doesn't really. First of all, it doesn't really matter. It's not really that important. But secondly, it's sort of the lowest common denominator. And Efi, whatever Efi you're running against, it will be guaranteed to support this size. So we create a blank image. At first, that's kind of like calling DD on Linux. You just create a blank image of the size. And then we insert the protective master boot record, which is this thing here. The protective master boot record is basically a sector, largely consisting of zeros, but it has a particular flag set, which is the OS type flag in the master boot record, this one here, and it's set to a value that suggests to any tool that reads this that this is a protective partition. What that means is, if you don't understand it, don't touch it. So the master boot record is there so that if you load it up in the disk repair utility, the disk repair utility won't deem it to be invalid and overwrite it and destroy it. It will see this and go, okay, I'm going to stay away from it because it's a protective MBR, and if it doesn't understand the rest of the disk, then it will not clobber it. So that's really important. That's why it's called a protective MBR. Right. Then we create the GUID partition. Again, I will not cover that in too much detail right here, but it is basically just filling in a structure, and lots of these numbers, like you can see here, are hard-coded. They are hard-coded because they are what the UEFI standard, which I'm referring to here, the UEFI 2.6 standard, is what they recommend. And there's no point trying to be clever, so just plunking in the numbers that they recommend is the safest option. And at the end here, after we create a partition and create some backup information, we go into, and this is the function I'm going to spend more time on, we go into the format EFI boot partition function, and we format it as FAT. So this is the function. What we'll do is we'll write a boot sector, then we will write the actual, a lot of calculation here, then we'll write some information only relevant to FAT32, if it is FAT32, and then we'll write the first FAT. If you remember from the image, in fact I could just bring that up again, these two both have two FATs, two copies, so they're basically, there's a backup copy of the FAT, and that's obviously used to recover if something's gone wrong. In our case, however, I'm going to elegantly bypass that and ignore it and just create a single one, the other one with 0. I could copy it, it hasn't proven to cause any issues. No disk tools are complaining, so I'm happy, and I won't try to be doing any more work than I have to. So ultimately, as I was saying early on, we will create this file structure here on this fat in this fat partition, EFI boot, and then the actual kernel file, and that's what the EFI bootloader will look for, and this is the structure it requires. All right, so to go back up again. There we go. As I said, the first thing we do is we write the boot sector. The boot sector is a standard structure. It contains various pieces of information, most which are not used because it is a Efi boot sector or Efi boot partition. But values still need to be valid. So this jump instruction that is used to jump to the code that is your bootloader, there is no bootloader code, but it needs to be valid because according to the standard, it needs to be valid. So if you are unlucky, you might encounter a Efi bootloader or some disk tool or whatever that will complain and ruin your day. So it needs to be valid. We also need to specify geometry information. So if you remember, for those of you who do, back in the day we used to have heads and sectors and tracks, or sectors per track. And this was information, geometry information used by interrupt 13 so that you could read a disk, and you needed to know how many reading heads it had. You needed to know cylinder count, which was a sort of vertical columnar kind of indexing of data, of sectors. You need to know how many sectors per track. It was quite a lot of information that was very specific to the actual hardware, the actual disk you were running. That information is no longer used. Today we use something called an LBA, or logical block addressing mode, and there's a good Wikipedia article about that. But you still need to fill in this information, and in fact, I guess it's again the same thing as with the boot sector. You know, you do need to have valid information if you run this if you use a tool on it, or if you try to open it up with something. I was running one file check tool and it complained, didn't want to load it. So might as well put it in there. These values, I suspect, could be anything because they're not really used unless you read this, but with interrupt 13, which no one will do today. But I took the table from this Wikipedia article, and hoping that at least it has some semblance of sanity. I suspect I could have put random numbers or made them all 42 and it would still work. Right, now we are going to decide what type of fat this shall be. And I said earlier that there was a heuristic that determined whether it was 32 or 16 or 12, which we're not supporting here. But there's also another thing which is pointed out in the document that Microsoft has created for FAT, which says that by default, Windows will try to create a 512, any disk less than 512 megabytes will be converted to FAT16, because it can handle it to FAT16. So the heuristic, the sort of involved heuristic that they are suggesting may be a little bit redundant if you can just use that simple rule of thumb. So I've followed that rule of thumb, and it's fine. Most of the time for the kind of boot images that I'm creating, I'll be running with FAT16 as the format. It's as good as any other decision, but it is the official decision. So it is the official Microsoft, thou shalt do this. If it is less than that, Windows will treat it as a FAT16, come what may. Yeah, so this is just filling out this extended boot parameter block. The extended boot parameter block, which continues beyond a certain point, offset 36 I think it is, in the boot parameter block, or the boot sector, or this thing that we filled up here. The reason why I'm umming and ahhing about the name is it seems to be called different things by different people. I call it boot sector. But we fill it in with various pieces of information. Key thing is that some of these are hard-coded based on the size of the sectors, 512 bytes, and based on the standards. Again, funnily enough, you have these fields that could be theoretically anything, but if you read the standard, it says for FAT16 it shall be 1, or for FAT16 it shall be 512. So who am I to argue? A random number provides us with the serial number, doesn't really matter. We fill in the volume label. Volume label is interesting. I didn't know this until I wrote this code. Another reason why it's nice to shave a yak occasionally. The volume label that's set in the extended BPB isn't the volume label that you see when you look at the disk. But if they're not the same, it will complain. A disk utility will complain. The volume label that you see on the disk is actually the one stored in the root directory. So it's the first entry in the root directory I'll come back to that. But probably as a piece of legacy, the volume label still has to be set inside of the BPB, and they have to match. There's also a file system type string, which is FAT16 or FAT32. You could put anything you like in there because, as I said earlier, that does not determine whether it's FAT16 and FAT32. All it does is to give it a name. But it is considered cricket and common courtesy to give it a name which indicates what kind of a file system it is. Oh well, so here we are. I am using a lookup table. Oops. Come on. Not wanting to do that. There you go. This is a lookup table that I have lifted from the documentation on FAT by Microsoft. Again, a little bit of magic, but what it is basically a mapping from the size of the disk to the size of the clusters. So how many sectors per cluster for a given size, for a given format. You could, in theory, put anything you like in here, but as always, if the standard says you should do it this way, it is probably a good idea. There will be tools out there that have hard-coded these or have made assumptions about them, so it's best not to be too inventive. So I just find which one it fits, which one it corresponds to, and I fill that in. FAT32 is very, very similar, slightly different numbers. So you can see here the reserved sector count is 32, whereas up here the reserved sector count is 1. In fact, if I go back to the diagram, let's see, yeah, this is a reserved sector count in this diagram corresponds for FAT16 just to the boot record, one sector, whereas for FAT32 it actually corresponds to a whole bunch of sectors that come here all the way up to the first FAT. But both of them share the fact that it's a number of sectors reserved before the first FAT. So, right, there's a couple of other things. Again, things like physical drive number, which is the standard hard disk ID here, OX80, probably not used by modern hardware or modern software even, but again, it's legacy, you have to put it in there. Same thing applies for FAT32 regarding the volume label. Again, it will be part of the directory, root directory, so this isn't technically needed, but it is needed to comply. And no, I do not support FAT12 yet. FAT12 is the one that is used for disks below a certain size, and it's usually used for floppy disks. And FAT12 uses 12 bits per cluster. I should probably have said that. 16-bit FAT16, 16 bits per cluster index. FAT32, 28 bits per cluster index, of course. And FAT12, 12 bits. And the downside to FAT12 is that clusters can span. Obviously, they're not aligned to 4-byte boundaries, so they can span sectors, and it's a bit tedious, a bit of bookkeeping to keep them up to date and to make sure that you are indexing them correctly. I just didn't have the time of the day to do that. This is an interesting one. I love this quote. That's from the Microsoft documentation. Do not spend too much time trying to figure out why this maths works. Okay, I'll take your word for it. This bit of code calculates the number of sectors you should allocate per FAT. For 32 and for 16, we have a fixed set of sectors for FATs. They can't grow, so we have to pick a number, and this is how you pick a number. And I guess you could argue that's a magic calculation, and in some ways it is, but I will take their word for it, and it seems to throw up and result in good numbers. So I'm happy with that. Right, some more to-dos here. Then the last thing to do from this initial section is to just write the actual boot sector. So that's a single sector, starts at LBA, logical block address 0, which is the first sector. I write one of them. This is a helper I have for writing using LBAs and doing all the seek and write in the back end. Not particularly clever, it's just making my life easier, and so that I don't have to litter the code with all the different calls to seek, then write, and then seek again, or whatever. FAT32 here has a sector following the boot sector, which is different from FAT16. It's the FS info sector. It contains a small structure which contains some signatures that must be of this form. I am not entirely sure whether there is any other sensible use for this structure than just verifying the format. So you could argue you could use it as a way of checking whether it is FAT32. But we write it as per standard. not really using it for anything other than just writing it and making sure that it is consistent, a disk utility will obviously complain, as it should, if it is wrong. Okay, so now we've written the first bits, written all these parts. So we've written whether it's FAT16 or FAT32, we basically filled up everything to the point of being ready to write into FAT1. So that's what we're going to do. And as I was saying earlier, we're going to create this file layout. So there are some calculations, what the first data LBA is. The first data LBA is the LBA where the data starts. In other words, this one here, first data LBA, so the first sector, effectively, where the data area starts beyond the reserved areas. And then we're going to calculate where the root directory will start. Remember, for FAT16, the root directory is part of the reserved pre-data area sectors. For FAT32, it's part of the data area, so these numbers will be a little bit different. And, okay, I'm going to be honest, this isn't the prettiest of code. It is very manual, because I'm going to scroll down a little bit. I'm actually deliberately, in fact, I didn't want to write this class where you can sort of, add directories, make directories, CD, all that, because that's total overkill for what I really need. All I need, I'll scroll down and show you, all I need is basically this stuff here. This stuff that, creates this layout, and it does it in a very manual way, as you can see from this code. But I actually deliberately, again, did not want to write a class which allows me to, traverse subdirectories, add things, etc. Because if I need that, I'll write it. But for this tool, I really don't need it. So why should I write it? It was hard, though, I have to say, to resist the temptation. So anyway, let's go back up here. Now, the first two clusters, FAT0, or FAT16.0, FAT16.1, same down here with FAT32, these two first ones here. These first are special in all the FAT formats. The first one has to include, has to contain the media descriptor byte in its lower byte, and the second one has to be the end of cluster marker. For FAT16, it's different from FAT32, because obviously FAT16 is 16-bit, FAT32 is 28-bit. I say that as if it's obvious. It's obviously not obvious, but it turns out FAT32 only uses 28 bits. And if you remember the diagram I had back here for the cluster, so I'm adding the cluster, the first cluster in the FAT for the root directory, for example, and it points to what the next one is, and the next one, etc. And the first, in our case, these clusters are only one long, so they immediately point to the end of cluster chain marker, and so do the Efi and boot ones. So basically, what I've said here is the directories I'm creating are all contained in one cluster each. They take up one cluster each, including the root directory, because I know I don't need more than that, and it's plenty. And besides, I'm not growing it, so it's all good. And so I just mark them up here. So I'm just punching into the FAT that these are the ends of the two directories that I know start here. With FAT32, I have a similar thing, but then I have the root directory. I'm going to point that out here with the cursor. So the first one is the root directory, the second one is the Efi directory, and the third one is the boot directory. Whereas here I had just the Efi directory and the boot directory, because the root directory is part of the reserved area. And then I basically build up the cluster chain inside of the FAT for the payload, the bootx64.fe file that I'm including. So I have the size of that file. Where did the size of that file come from? Oh yes, it's passed in, and I calculated the size of it here. Yes, here we go. I calculate how many clusters the payload takes. I round it up so that I have it by nearest sector, and I copy, as in I build up the cluster chain. So remember that each entry in the FAT cluster chain is the next cluster. So it's the next pointer. So that's what I'm doing. So I start with, this is why there's a 1 here, I'm not starting with 0, right? So I start with FAT16, first cluster, let's say cluster, start cluster for the boot x64.fe files is 4 in this case, because I have two reserved entries, these two guys here, And I have two clusters for Efi and boot, these two here, so that's offset 4. And the cluster entry in the FAT for the first one, 4, points to the next one, which is 5, presumably because the file is bigger than one cluster. It may not be, but assuming it is. And then it keeps going around the loop and doing this, and every time it hits the max clusters per sector, we have to write it out because, remember, the FAT can contain many sectors, and the file might be big enough that it spans multiple sectors for the FAT. There's a lot of use of the word FAT here, and a lot of use of the word cluster, and I realize it is a little bit confusing, but I do hope that it makes some sense. We are just building up a linked list effectively here, based on the number of clusters we need for the payload that we're going to save to disk. But remember, this isn't saving to disk yet, so the contents of the file are not saved yet. We're just building up the FAT linked list of cluster pointers for the file. All right. And the same, very similar for FAT32. I could probably have combined these two into some sort of helper function, but I didn't. It's different enough, and you can see here stripping off the top 4 bits because that's what FAT32 does. All right, so now I'm going to actually create these directories and files. I already alluded to what I was doing down here, but the first thing I'm doing is to create the actual the volume label, as I mentioned earlier. The first entry in the root directory is a special entry which has an attribute called volume ID. There can only be one of these, and that's where the volume label lives. So it's like a directory or a directory entry, but a special one, and its name is the volume label, and that has to match the volume label that we set in the extended BPV earlier. Then I add the EFI directory, which is a normal directory. I use this little next cluster, which is kind of like a next free pointer. This is where it starts. So next cluster is where that directory starts. So we have the Efi directory. This is a pointer to the Efi directory. The Efi directory itself is in the value that next cluster has here. I save that because I'll use it later on. This special directory in the root directory, by the way, we do not have dot and double dot directories. If you'll know this, or if you don't, have a look at your C colon. You'll see you don't have double dot and dot directories because the root directory doesn't have that. And then we create the contents of the Efi directory, which is in its own cluster. So we have to. This is a new sector that we're going to write into a new cluster, and we sort of repeat the process. But here we have dot and double dot because this is a normal directory. All right. So we add into that directory the boot directory entry, which is also a directory, and it starts to whatever value next cluster has at this point. Then we write that out to disk. Then now we have the two directories EFI and boot, and now inside of the boot directory we are going to actually write the contents of the boot x64.efi file, in addition to the two friends dot and double dot. All right. There's a little bit of calculation here. This function cluster to LBA, I should point to that. So this method, this function is lambda. It calculates the actual starting LBA given a cluster. And because the two first clusters in any of these file formats, FAT16 or FAT32, are reserved and used for other things, to store information, we have to subtract 2 and then multiply by sectors per cluster and then add first data LBA. That gives us the sector for the LBA for a particular cluster. So we're using that down here to calculate where these different, like here for example, the boot directory, that's the directory called boot. That starts at some sector given by the boot dir cluster, and the payload, the boot x64.efi file, starts on sector whatever it is given by boot x64 start cluster. And then we just do a simple, fairly noddy and unadventurous copy into the clusters. So we fill up the clusters, the cluster chain. It's very simple because it's a linear, everything's linear here. We haven't, added or deleted files, or there's no fragmentation, so we can just start at the beginning and just keep writing this file to disk, starting at the first cluster. We don't have to even traverse and move around anywhere. We can just start at the first cluster and write it out. And it will map, because this boot start cluster is exactly the same one as we used up here. This guy. This will just map magically. It will just work. Oh, it's not magic, obviously, but it will work. And that's it. We've written it. We've written the master boot record. We've written some information. We've written the FAT, which just lays out this particular structure. This particular directory structure that we want, this hard-coded one. Again, this is very specific, a tool written only for doing this. And at the end of that, we will get something that we can load up. So let me actually try some. This is another thing I didn't know. 7-zip can load these images. I did not know that, but it can. Look. So 7-zip, I can click on the boot.dd file that my tool has generated. There's the Efi folder. Lo and behold, the one we created. There's the boot folder, and there's the kernel file. Look at that. I can even open that, I think. Yeah, there you go. See, 7-zip, if you didn't know this, I mean, I was quite impressed by that, actually, that you can do that in 7-zip. And that's it. We have a tool, we have some source code, and if you want to look at it, you can have a look at GitHub/Jarl Ostensen. That's my GitHub repo. And there's a repo there called JOSX64, which is where all of this stuff happens. It's my little pet project to do a UEFI kernel, 64-bit UEFI kernel. I've done some kernel work before. I have a 32-bit OS project on GitHub as well that I've been playing with, but I wanted to advance into the world of 64-bit and UEFI, or Efi, and that's what I've done. So thank you very much for listening. I hope there was some usefulness to it, and until next time.